There are two physically different types of solar panel, or sometimes referred to as photovoltaic or PV panels. There is a rigid glass and metal bodied variety, and there is the semi-flexible plastic sheet type variety. And there are four major types of solar panel cells, that being the solar cells that are used to make up a solar panel. The different types of cell are thin film, polycrystalline, monocrystalline, and monocrystalline PERC that are used to make up solar panels, and are being sold on the market presently in 2023. PERC, just for the sake of it, stands for passivated emitter and rear contact, or passivated emitter and rear cell. How these cells work is outside the scope of this tutorial. I'm just going to point out some of the pros and cons of what might be looked for when purchasing solar panels and how we might wire them up and attach them. Which solar cell is the most efficient? That's hard to say exactly. The polycrystalline is probably the lowest performer. The monocrystalline PERC is probably the best middle market performer. After that, there are a number of specialty types of monocrystalline solar cell that offer slightly greater performance and efficiency, graded in percentages, up to about 22.8% and often rounded off up to 23% efficiency for the best solar panels on the present 2023 commercial market. But on average, you might consider anything from 15 to 20% efficiency a decent figure. The efficiency rating is often marked on a label on the back of the panels, along with other relevant information. Solar panel efficiency is based on how much captured sunlight can be turned into actual electricity. As I said earlier, 22.8% or rounded off to 23% seems to be about the best you can get in 2023. All the aforementioned solar panel type tend to come in square or oblong, flat or flattish format. Each type has its own unique advantages and disadvantages. The solar panel type best suited for your installation will depend on your preferences and factors specific to your particular project and environment, and of course your budget. I will cover here just the most common applications of solar panel usage in 2023. Please see my other tutorials for more information on how to wire up a solar panel or panels to a solar charge control unit, which you really should use as an intermediary device between your solar panel array or solar panels and a leisure battery or battery bank. Rigid or flexible solar panels. It depends on your application. Clearly, the glass solar panels will weigh more than the lighter weight plastic ones. However, I will point out that the glass panels will last longer and usually have a longer warranty than the plastic variety. Glass solar panels will also work a little better than their plastic cousins. So it's a horses for courses kind of thing. My suggestion would be go with the glass solar panels unless you have to go with the plastic semi-flexible panels. The glass panels tend to be cheaper than the plastic panels. If you're planning on a stationary application, again glass would probably be the better choice. However, for a vehicle, it's a case of what will work. I have a pop-top roof on my VW camper van that lifts up at a diagonal angle on gas-filled struts. So I needed something lightweight and I wanted something also low profile so that I could just still get under height restriction barriers in car parks and drive-thrus. So I went with plastic, as it would sit lower on my roof and be lightweight. As plastic panels are a little more complex in their build types and glass panels are pretty much all the same in their build type, I will spend more time on explaining the nuances of the plastic panels. However, some of those nuances will also apply to glass panels. Keep in mind, as a rule, plastic panels don't flex all that much. Maybe just a few degrees, enough flex for a vehicle rooftop, but not a whole lot more. You should not try to force them to flex more than a few degrees, as this will often break the internal workings of a solar panel. Remember, they're pretty fragile and brittle sheets of silicon, which is a kind of thin-baked stone inside of them, and can break easily if not handled right. They're usually okay when they are stuck down and not being flexed, but just try not to flex them or bend them too much. And if you're bending them a little, only bend them in a concave way, so that the sunlight side is on the outer curve of the bend. There are different plastics used for flexible solar panels. What you should look for, as of 2023, is a transparent ETFE type plastic top layer that is matte in luster, that being not too shiny or reflective. Some better quality plastic solar panels have very small pyramid-like mouldings on the ETFE transparent top layer, designed to capture and refract more sunlight onto the solar cells that are under the ETFE covering. But whatever the cover is, you want it to be sturdy. The ETFE type of plastic is the best there is at this present time, and you don't want anything shiny and reflective. A matte surface will also absorb more sun rays. A shiny reflective surface will reflect the sun rays away, so you don't want that. Some cheap, no brand name, eBay, Alibaba or AliExpress purchased panels can be very shiny and flimsy. Be careful not to bother too much with these panels. They're usually just a waste of money. From personal experience, I do believe it's best to go with panels being distributed distributed by an established company, and be willing to pay just that little bit more rather than chancing your arm on cheap solar panels. A good reliable warranty and guarantee from a reputable company is what you really want. Do your research before purchasing online. There are a lot of junk solar panels out there, and there's many people selling them. Just because they are made in China, as by and large most of them are, doesn't dictate the quality. However, an official agent or retailer in your country of purchase that you can contact if there is a problem is preferable. Then you might want to have someone you can go to legally after in the event of a possible failure. For semi-flexible panels, you might want to look at around a 5-year warranty on materials and workmanship. That's about as much as you might expect. You can double that warranty period for rigid glass panels, but again, make sure it's from a company with a good reputation that will genuinely stand behind their solar panels warranty. My suggestion is try to contact the company's solar panel warranty personnel by phone or email before purchasing the panels, just to see if their support personnel actually respond. Many of them don't. Therefore, stay away from their panels. The solar cell type in the panels you acquire is up to you based on your budget and general requirements. The materials used for solar cell backing can be any number of different types of plastic, from PET backing PET on the cheaper solar panels to middle market fiberglass TPT or even ETFE used as a backing material, as well as being used as a face material that is used on the significantly more expensive panels. Remember, the panels may well be subjected to significantly extreme weather conditions and heat, so the quality of fabrication and materials used is of great importance. The layers of the panels often being glued together on the better brands by an EVA type glue. PET or polyurethane type backing sheet is not as heat resistant as fiberglass or TPT, so air pockets and cracks tend to form on the PET back sheet after just a few months, because PET is a thermolayable plastic and easily swells in high temperatures. So try and stay away from cheap solar cells with PET plastic backing sheets. Fiberglass or TPT is generally the best middle market choice, and ETFE as a backing material as well as a face material, if you can find it, is about the best. PET or polyethylene terephthalate is the poorest performer, that is PET. Fiberglass is the best middle market compromise, or TPT, Tedlar polyester Tedlar, is the best but quite expensive, or ETFE, if you can actually find it, would be the best backing, but you don't see it too often. How to attach your solar panels. There are fairly decent kits for attaching rigid glass panels to stationary roofs and to vehicle roofs. Just do a Google search for solar panel attaching kits. Note, obviously, the more physical attachments that you have to hold the panel to your roof, the better. However, semi-flexible panels are a slightly different matter. One thing you should keep in mind when attaching solar panels is ventilation. You should do your best to allow some airflow under the panel. Many people, when attaching flexible solar panels, use a polyurethane type glue product like Sikaflex that comes in a corking tube to adhere their panels to a flat smooth roof, and this seems to be a fairly common way of attaching the semi-flexible solar panels. Sikaflex, you owe me for the mention. My suggestion is, and this applies to all methods of adhering semi-flexible solar panels to a smooth vehicle roof, keep ventilation in mind. Normally, I would run heavy lines of polyurethane type glue at about 4 inches or 100mm apart, perpendicular to the travel of the vehicle. That way, the airstream when the vehicle is in motion won't try and lift the panels off the roof. However, the panels will still allow some airflow under them. It is best when gluing to keep something of a gap under the panels to allow that airflow between the lines of glue. This will allow your panels to work better, as solar panels don't really like to get too hot. There are varying methods of gluing the panels down whilst retaining a small gap under the panels. Quickly, I just want to point out that the wiring junction boxes that are attached to your solar panels can be manufactured on the underside or the top side of the solar panel, so be sure to keep this in mind when purchasing solar panels. You don't want to be trying to attach them to a flat roof only to find that it is not possible due to the solar panel's wiring junction box being an obstruction if you're adhering a flexible panel with glue or tape. That junction box holds a couple of needed diodes that make sure the electric current only leaves the solar panel and doesn't reverse back into the solar panel out of your battery or solar charge controller and turn your panel or panels into glowing nightlights. So again, be aware of what what side of the panel the wiring junction box is on when purchasing solar panels. Usually on rigid panels it's on the back, and on semi-flexible panels it's on the sun-facing side, but not always, so be sure to check before purchasing. Personally, I have found that using heavy-duty Velcro tape has worked for me when attaching semi-flexible flat solar panels. This allows for easier removal of the solar panels if needs be, but not too easy. You don't want anyone easily stealing them. I tend to run my Velcro tape in line with the travel of the vehicle so that air can get under the panels and cool them down whilst I'm in transit. I'm pretty confident in the tape's holding ability as it is heavy duty, yet I have still stuck a small wind deflector located just a little in front of the panels to deflect the wind over the panels whilst the vehicle is in motion. If you're sticking the flexible variety of panels down on a boat and the panels might be walked on, then it would be better to put quite a lot of polyurethane type glue down so that they won't flex if stood on, this creating a sturdy base and not allowing the panels to flex too much, making the panels more durable underfoot, as you might have to live with the fact that the solar panels could still get broken underfoot or from overheating and be ruined prematurely if there is any flex in them from being walked on. So you might consider doubling up your glue lines, like one every 2 inches or every 50 millimeters. I personally have a pop-top roof on my camper van, so when I am stationary and the roof lifted at an angle and the panels angled up at the sun, the heat of the air under the panels will evacuate from the upper edge of the panel due to convection, heat rising, drawing in cooler air from the lower underside of the panels. This gap being created by the thickness of the heavy-duty Velcro tape. This method I have used quite successfully on the pop-top roof of my VW T5 camper van. Just for reference, Velcro tape is sometimes referred to as hook and loop type tape. If you go this route, be sure that it is the genuine Velcro heavy-duty variety of hook and loop tape. I personally can only endorse the Velcro heavy-duty brand, as that's all I have experience with. You heard this idea first from me. Velcro, you owe me for the endorsement. So, that's how to attach your panels. Now, onto the wiring and the connections. Firstly, any external cable wire type used will be exposed to the weather elements and primarily the deteriorating factors of UV sunlight. Solar cable wire is a special kind of cable wire. Most solar panels will come with a couple of short lengths of this special UV and weather resistant cable wire already attached to the solar panels, probably with MC4, that is MC4 type water resistant plugs or electrical connectors. Make a note of the wire already being used with the panels, as this is the gauge or thickness of wire, that is the very minimal gauge that you might use when further wiring your panels to a solar charge controller. Sometimes the gauge or thickness of the metal conductor factor of the cable wire is printed on the wire sheath. Sometimes you will have to look at the manufacturer's specification sheet or their website, or if you're lucky it is indicated on the specifications label on the back of the solar panel. UV sunlight resistant cable is most commonly 4mm2, which the latter number 2 means squared, that being a decimal form of measurement. However, it also comes in 2.5mm2 and 6mm2. Again, the little 2 at the end would mean squared. Note, you don't have to use UV resistant solar cable all the way from your solar panels to your solar controller. Once your wiring run is out of direct sunlight, you can revert maybe using a junction box to a regular sheathed or insulated wiring, as long as the connector, the metal part of the wire, is the same gauge or thickness as the solar wire, or even a bit thicker. So, wire that's out in the elements needs to be UV type cable, and once you get inside, then you can use regular type cable wire, as long as the gauge of the inner part of the wire, that is the metal conductor part, matches the same gauge or even heavier than the gauge of the wire being utilized on the solar panels. Now, onto the wiring methods. This is not all that complex once you grasp the concept of parallel and series wiring. It really is actually quite easy. I'm going to use 4 100-watt semi-flexible solar panels in order to aid with my descriptions for the following graphic illustrations and examples. I suggest that you check out my number 3 DC Electric Basics tutorial for what watts actually are, if you don't already know. In short, watts are a calculation of volts times amps, or amps times times volts. I'm going to point out here, in the electrical world, amps are often represented by the letter I, like a capital I usually. I know amps are spelt with an A, but for some reason in electrical jargon, the convention is to use the letter I. I believe it's a continental or French thing. Ooh la la. Please see my number 3 electricity basics tutorial. So again, watts are a calculation of V times I equals W. That is, volts times amps gives you watts or wattage. Or it can be done the other way around. I times V equals W. Amps times volts gives you the watts or wattage. Confused yet? Then try this. Watts or wattage, same thing, divided by either the amps or volts will give you the figure of one or the other. For example, 400 watts divided by, let's say, 24 amps gives us 16.6. So that would mean the voltage is 16.6 volts. Okay, let's say we know the volts are 16.6 and the watts are 400. So we divide 400 by 16.6. We get 24. That would be 24 amps. Sometimes a calculator helps. There might even be a calculator on your mobile smartphone. Okay, so we know how to calculate the solar panel figures. That is, if we had all the figures in the first place. But in this scenario, all we know is that we purchased 4 times 100 watt panels, because that's what they're called when we bought them. This is when we look on the back of the panel, or on the box that they came in, or the leaflet that came with the panel, or on the website where you purchased the panels from, because there is some pretty important information that will help us configure the panels optimally. That information on each panel might be somewhat similar to this. Note, these are just example figures for educational purposes. Also, the specifications are not always in the same order as this example, and there can be additional terms and numbers that we don't really need to bother too much with. One other point being, it would seem that some solar panel manufacturers' noted specifications information doesn't always follow the standard nomenclature or wording, or do they use the standardized abbreviations? By using this tutorial, you might be able to figure your way around this by understanding the fundamentals of how the figures work together. Okay, so I'm going to give you some examples. Pmax equals 100 watt power maximum. This being the maximum electric generated by the panel under ideal sunlight and ideal temperature conditions. So that would be Pmax, P-M-A-X. VOC. Now in our scenario, we're using 17.9 volts. So VOC stands for, in this case, would be 17.9 voltage open circuit. This is used more for panel testing purposes. It's not something you really need to be on top of. But if you're making tests using a multimeter, then VOC, we'll go into that later. Then there's VMP. In our case, we're going to call it 16.6 volts. Maximum power, that is. So VMP stands for voltage maximum power. This is important for configuration. Keep the VMP in mind. Then there's ISC, which in our case, we're going to say 6.24 amps for the example. It stands for amperage closed circuit. Again, the I stands for amperage because it's an electrical thing. So IMP stands for amperage maximum power. In our case, it's going to be 6 amps. And this is important for configuration. So keep the IMP and the VMP in mind. These are important. Then it might have UL or CSA or VDC. It stands for voltage direct current, which is the maximum voltage that the panel can handle being channeled through it. That is usually a pretty high voltage number and is only taken into account if you plan on attaching a lot of solar panels in series together. Then there's the efficiency, which I mentioned before. In our case, this example, we're going to call it 18%. This is the panel's ability to turn sunlight into electricity. 18% is about the median average. Anywhere from 15 to 22.8 is what is available as standard as of the year 2023. So the most important numbers for us to look at for the sake of the wiring connections to and the purchase of a solar charge controller are the VMP and the IMP, or voltage maximum power and amperage maximum power. The other two figures, the VOC and the ISC, are more for testing the panel if you have an electrical testing multimeter. These figures are there so the panels may be tested before they are wired up, because when the panels are wired up, they will give different electrical power results than they will when they are not wired into a circuit with a load. A load is when something is wired to the solar panel in a circuit and electrical power is actually being channeled through the circuit from the solar panel to a load. A load will suck that power, hence it will draw down the voltage to a degree. More on this in a little bit. When looking for or at the numbers, you want to look at the lower voltage and the lower amperage numbers stated on the solar panel's specification document, or the label adhered to the back of the panel. These lower VMP and IMP numbers are the most relevant to our calculations. There are usually two amperage I figures given, a lower IMP and a higher ISC amp number, and the two voltage V figures given a lower VMP and a higher VOC. We're just going to use the lower two numbers of the two different electrical power definitions when figuring out and calculating what rate our solar panels are going to give us. Wiring methods. As I might have said earlier, there are a few different wiring methods that you might employ. One being a single panel with a simple positive and negative connection to the solar charge controller. However, if we have two panels, we could join both the positive wires together using a three-way wiring connector and have a single positive cable wire running off of the three-way connector. That could run to the positive solar charge controller screw down terminal. This method applying to any number of like wattage panels. The same would apply to the negative cable wires, basically bundling all the same polarity wires together to form a single wire. This is called parallel wiring. What this does is maintain the same voltage of the single panel or a single panel regardless of how many panels we combine. But what does happen is the amperage of each individual panel is multiplied by the number of panels that we are connecting up in this way. So, using the earlier example of 4 times 100 watt panels rated at 16.6 volts VMP each at 6 amps IMP each, then our combination of 4 panels wired in parallel would give you a maximum, assuming the panels were all getting full sunlight, 16.6 volt VMP at 24 amps IMP, because we've got 4 panels at 6 amps each. Now, if we were to wire these same 4 panels in what is referred to as series wiring format, we would get a somewhat different electrical power outcome. If we connected the positive wire from each panel to the negative wire of the next panel, effectively linking all 4 panels to one another in a chain, leaving a single positive wire and a single negative wire at the ends of the chain, then we would end up with 2 cable wires that would, if connected to a solar charge controller, from our example, calculate up to give us 4 times 16.6 volts would equal 66.4 volts VMP at 6 amps IMP. You see what happened there? Depending on how you wire up the solar panels will result in different volt amp outcomes. Technically, however, if you calculate the outcomes any which way, you will come up with the same wattage, but we're more concerned with the voltage and amperage, VMP and IMP, for the time being. For your information, the solar panel overall wattage is based on a calculation of the VMP and the IMP, not the VOC and ISC. Remember, it's the VMP and the IMP multiplied will give you the wattage of the panel. Solar controllers are generally rated on their amperage and voltage handling abilities. Please see my tutorial number 8, Solar Control Basics. In short, there are 2 different kinds of solar charge controller on the present 2023 market. Both handle the electric charge coming from the solar panels differently. In short, the PWM solar charge controller will only limit the voltage being sent to the battery or battery bank to a level that is ideal for the charging of the battery based on the battery's chemistry. The PWM controller is not so good at regulating the amperage or IMP. It's the amperage that tends to heat things up and cause issues with a battery charging scenario. So, using a PWM solar charge controller, you would have to wire your solar panels up in such a way as to keep the amperage at a level that your batteries can handle without the battery or its connections getting overheated. In my personal case, with one 100 amp nominal 12 volt LiFePO4 battery that's lithium phosphate, 18 amps seems to be the amperage limit the battery can take before things start to heat up a little. So, if I were using a PWM controller, I really wouldn't want more than 3 solar panels rated at 16.6 volts VMP and 6 amps IMP each wired in series, creating 16.6 volts VMP at 18 amps IMP. However, there is another sum that should be calculated into the PWM equation, the 1.25 PWM rule. Please see my number 8 Solar Controller Basics tutorial for more on this rule. I would probably use an 18 amp fuse between the solar panels and the solar charge controller, as I live in the northern hemisphere and would seldom if ever have the panels getting 100% sunlight. So it's a risk I would take, gambling on the panels never being pushed beyond 18 amps IMP. Please see my number 8 Solar Controller Basics tutorial. But as it is, I use an MPPT solar charge controller, which is somewhat more sophisticated than the PWM solar charge controller. Again, please see my tutorial number 8 Solar Controller Basics. In brief, an MPPT solar charge controller is wired up pretty much the same way as a PWM solar controller, primarily a positive and negative cable wire going from the solar panel or panels to the solar charge controller, and a positive and negative wire running from the MPPT solar charge controller to the leisure battery or leisure battery bank. Please see my number 5 electrical wiring tutorial. Differs the MPPT solar charge controller from a PWM controller is you get more control over the electricity generated by your solar panels. The MPPT solar controller has a few extra tricks up its sleeve to squeeze some more electrical power from your solar panels by using algorithms and stuff. Can't even say the word. In all honesty, I don't even know what algorithms are, but here's the general gist of it. When electrical watts are created, there are two factors, electrical voltage and electrical amperage, that make up wattage. Please see my number 3 electric basics tutorial. Depending on how you wire up your solar panels, we can optimize the voltage or the current, that is the amperage, or possibly find a nice working balance between the both, between voltage and amperage. More on this in a bit. The better MPPT solar controllers will monitor and measure what the leisure battery or leisure battery bank needs in order to be optimally charged. Always monitoring via an internal computer. But here's the kicker. Let's say the leisure battery only needing a maximum of 14.4 volt charge being sent to it. However, our solar panels are creating a greater voltage, let's say 16.6 volts or even more. Then the excess voltage over the 14.4 volts should be converted by an MPPT solar controller into amperage or current. That will go along with the voltage to the leisure battery, charging the leisure battery more better or optimally. Now, here's where it might get a little weird, but not that weird. I'm using my setup as an example. As I stated before, my LiFePO 4 leisure battery can only really handle 18 amps IMP or before it starts to heat up. I have 4 100 watt solar panels generating 16.6 volts VMP at 6 amps IMP each. I have paired 2 of my solar panels together effectively twice, both pairs being wired in series, creating what might be thought of as 2 single solar panels working at 33.2 volts VMP and 6 amps IMP. Then I have further wired both of those pairs of solar panels in the parallel wiring format. So therefore, technically, I am creating in the whole array 33.2 volts VMP at 12 amps IMP. The practical reasoning behind this being, 1, it was easier to cable wire them this way for cable wire layout practicalities. The higher voltage I have created by combining 2 of my panels in series tends to travel the longer distances better through my camper van to my solar charge controller with negligible voltage losses due to the higher voltage. Because my solar charge controller is located as close to my battery as I could practically manage, yet still some distance from my solar panels. By combining the 2 pairs of solar panels, I also give myself a decent amperage to charge the battery or battery bank. Again, see my number 3 electric basics tutorial. Keeping in mind that the excess voltage will be converted into amps anyway, because I'm using an MPPT type solar charge controller. So I kind of have the best of both worlds. Although my solar panel amps are lower than the 18 amp threshold that I have configured as my battery charging limit, the combination of the amps generated by the solar panels, if they ever get optimal sunlight, and the extra amps converted by the excess voltage should be within the 18 amp mark. If it goes over, the MPPT solar charge controller will restrict and limit the amperage being sent to the leisure battery or leisure batteries. This restricting of amperage current is not something a PWM solar controller can do. PWM controllers usually only control the voltage. Again, please see my number 8 solar controller basics tutorial. So, there is no real all-encompassing better way of wiring your solar panels. There are just different ways that will work better in some scenarios than others. I tend to go for the middle ground, covering as many bases as possible by mixing my wiring up between the 2 wiring methods, that is series and parallel. As I have 4 panels, wiring 2 panels in series and then 2 pairs of series wired solar panels, then wired in parallel. There is one small thing that might be a concern to some, that is shading on your panels from a tree or something like that. Partially covering a panel when grouped like this. If your panels are all wired in parallel, then a little shade or any shade on any one panel probably won't affect all the panels and bring down the overall power created. However, if your panels are all wired in series, then one panel getting some shade from the sun due to some kind of obstruction will bring down the power generated by the whole array of panels. It's just the nature of the wiring, just saying. One other thing being, if you have panels of different wattages, regardless of how you wire them, the power output from a group or array of panels will always be limited to the lowest rated panel. In this kind of scenario, you might look into using multiple solar controllers, a different controller for each of your different rated panels.
How to test solar panels with a multimeter. So how do we test solar panels? You're going to need an electrician's multimeter, as we will need to test both the voltage, VOC, voltage open circuit. This figure is usually just used for panel testing purposes. And we're going to need to test the amperage, ISC, amps short circuit. This figure is usually used for just testing purposes also. An electrician's clamp type multimeter multimeter would be ideal. However, I will describe how to do the tests with the more common regular electrician's multimeter. So using our earlier solar panel setup of 4 100-watt panels, we're going to test one panel at a time. Each panel has a VOC and an ISC figure associated with it. You should find these figures possibly printed on a label on the back of the solar panel, or on the box the panels came in, or on a leaflet supplied with the solar panel, or maybe on the retailer or manufacturer's website. Remember, we are looking for the VOC and the ISC, or voltage open circuit and amps short circuit. Unfortunately, not always using the exact definition that I've given here, but similar. You'll figure it out. The numbers we are going to use specifically for this example are a VOC of 17.9 volts and an ISC of 6.27 amps. VOC 17.9 voltage open circuit, ISC 6.27 amps or amps short circuit. These, or something like these figures, are what we are going to be looking for displayed on our electrician's multimeter. Firstly, we need to lay the solar panel out in the sun somewhere. If it's a flexible panel, try to lay it out without flexing it, preferably facing the sun. However, we will need to be able to get to the wires. We will also need to cover the panel with a piece of cardboard or a towel or a blanket so no light gets to it, just for the time being. We now need to configure the multimeter, making sure the testing probe plugs are located in the correct sockets on the multimeter. The black multimeter cable wire with a testing probe on the end usually connects to the COM or common cable wire socket on the electrician's multimeter, and the red multimeter cable wire with a testing probe on the end in this particular test needs to connect to the V or voltage measuring socket on the multimeter. Set the electrician's multimeter to measure DC voltage. In this particular case, on my multimeter, I'll set it to 20 volts, which should be the nearest, maybe slightly higher voltage figure to which you are trying to test. We need to touch the black wired probe running from the electrician's multimeter COM socket to the negative marked short cable wire coming from the solar panel, and the red probe from the V plug of the electrician's multimeter to the positive cable wire of the solar panel. You might need two sets of hands here. Then, removing the covering blocking out the light from the solar panel, if the sun is decent, you should get the full, in our case at the moment for the test, 17.9 volt or whatever VOC is noted as on the documentation. Now on to testing the amps or the current, same thing. This is a bit more complicated. First thing is check does your multimeter test amps? Most do. However, very important, is the multimeter that you are using rated to test the amps? Is it above the ISC figure associated with your solar panel? Be sure that the multimeter that you are using is rated above the ISC figure of the solar panel, or you may damage the multimeter. Most multimeters will indicate their amperage maximum rating, like 10 amps or 20 amps. In our case, as our ISC is a maximum of 6.27 amps on any single panel, then a 10 amp multimeter should be just fine. You may also have to move the red testing probe plug over to another terminal socket on the multimeter, as we are now testing amps and no longer testing volts. Also, as we are testing amps, you will have to configure your multimeter to read amps instead of volts, which may be represented by an A on the multimeter dial. Again, 10 amps will cover us in this example scenario.
So, now we have the multimeter set up to test amps, or, to be more specific, the ISC, or amps short circuit. Again, be sure that your solar panel is covered with some kind of covering like cardboard or a towel or a blanket, and that the panel is situated in such a way as the sun will shine directly onto the face of the solar panel when the covering is removed. Connect the black probe wire coming from the COM socket of the multimeter to the negative cable wire coming from the solar panel, and connect the red probe wire from the amperage, or A socket of the multimeter to the positive cable wire coming from the solar panel. Then wait for the sky to absolutely clear and the sunlight shining directly at the panel. Then gently and fairly slowly pull the covering off the panel without disturbing any of the wiring. You should now see a figure that is fairly close to the ISC figure as given by the manufacturer, represented on your multimeter. It's best not to expose the panel to too much sunlight whilst in this configuration, so as soon as you've gotten your amperage or ISC reading, you should cover the panel over again, as the flow of amps and current current in this short circuit configuration will put the multimeter and its testing wires under some stress. We don't want to damage the multimeter or its testing wires. This test shouldn't harm the solar panel if done for less than a few minutes. The reason for covering the solar panel and then slowly exposing to the sunlight when doing this test is so that we don't get a surge of amperage or current that some multimeters might not like. Sometimes, for a fraction of a second, if the panel has been left exposed to the sunlight, electric power accumulates in the panel, and when you attach the testing probes, a fairly large wave of amperage current rushes to the meter and blows its fuse, if it has one. Just keep that in mind. So, I hope this helped somewhat in your choice of solar panels and what to consider when buying and building your solar power system. Don't forget to like and subscribe. I believe I've got everything correct here. However, I am human, so it's possible I might have made a mistake. So keep it real, comment if you wish. Much love and happiness to you all.